I'm the Interim Vice President for Research at Utah State University. Sunrise sessions are just one of the ways that we in the Office of Research at Utah State share the best of our research and our researchers and highlight the impacts they are having on Utah. I'd like to start today by thanking Regents for sponsoring these sessions. Their partnership with Utah State University maintains its commitment to research and outreach. With us today from Regents are many friends. They include Jim Swayze, Miguel Rivera, Eric Hales, Amy Kahn, and Kayla Norman. Thank you all for being here. As many of you know, USU has been celebrating the Year of the Woman in 2019. Here is a very brief video intro of what this year is all about.
"2020 marks anniversaries that dramatically changed Utah and our nation. While our country celebrates the 100th anniversary of women's suffrage, Utah celebrates its 150th anniversary since Seraph Young cast the first ballot by a woman. This next year also marks 55 years since the Voting Rights Act of 1965 legally removing racial discrimination at the voting booth. To commemorate these historic events and contribute to state and nationwide celebrations, Utah State University declares 2020 the Year of the Woman.
USU's Year of the Woman will highlight exceptional women from the past and today who have contributed to Utah State, their communities, the state of Utah, and beyond. This Sunrise session marks our first of 3 special sessions designed to commemorate the Year of the Woman. We are featuring 3 of our exceptional female researchers who are impacting the world with their work. You can view all 3 of these researchers on the handout that is on your table. Today, we are going to hear from Dr. Alexis Ault. Alexis received her bachelor's degree from Wellesley College and her PhD from the University of Colorado. She was a postdoctoral fellow at the University of Arizona's Department of Geosciences before coming to Utah State University. With innovative tools and technologies, Alexis' research team at Utah State studies fault rocks that have moved over time throughout the Earth. Her findings have led to insights on the mechanics and history of earthquakes on our own Wasatch Front. In 2017, Dr. Ault received the prestigious 5-year NSF Career Grant, which is awarded to top faculty throughout the country. This award is helping her to develop new textual and thermal-chronological tools to identify past earthquakes. Alexis is also the recipient of a 2019 Early Career Award from the International Standing Committee on Thermochronology. And in 2018, she was the USU College of Science Researcher of the Year. Since arriving at Utah State University in 2014, Alexis has published 14 papers in leading scientific journals and has been invited to speak at 9 international conferences. I'd like to share a brief video with you featuring Dr. Ault and her work.
My name is Alexis Ault, and I am an assistant professor in the Department of Geology in the College of Science here at Utah State University. Earth processes are thermal processes. For example, when an earthquake occurs, most of the energy is given off in the form of heat. And what I do is I integrate textual observations with thermochronology to back out that record of heat in earth processes. A big part of my research program is mentoring, and mentoring the next generation of earth scientists. And that includes the undergraduates that I integrate into my program, as well as graduate students and postdocs, and work that I do with the Native American Student Mentoring Program and middle school students. Thermochronology can quantify erosion of the Earth's surface and mountain building events that happen on the scale of tens to hundreds of millions of years. And so I use thermochronology to back out the record of those processes. This is important for the study of earthquakes and modern seismic hazards and resource development and sustainability.
And with that, I would like to welcome Dr. Alexis Ault.
Well, good morning, everyone. Thank you all for coming and for having breakfast with me today. I want to thank Lisa for inviting me to speak and to the Board of Regents for supporting this event. I am excited to be here this morning to talk to you about one component of my research program at Utah State University in the Department of Geosciences. And that focuses on earthquakes and the rock record of earthquakes. So earthquakes occur on faults at depth within the earth. And those fault rocks act as tape recorders, keeping track of the processes that are happening as earth materials deform and as seismic energy radiates through the subsurface of the earth. So my research program studies those fault rocks. We're sitting here this morning in Salt Lake. This is a photograph of the skyline that we might see outside. Salt Lake is a major metropolitan area along the Wasatch Front, the Wasatch Corridor. And the Wasatch Corridor houses over 80% of Utah's population. Now, when I look at this photograph, what I see is the stunning skyline behind the urban environment. This is the Wasatch Mountains, and sitting along the base of the Wasatch Mountains is the Wasatch Fault. Many of you know that the Wasatch Fault is capable of hosting earthquakes. It is what we call a seismogenic active fault system. This fault runs from up in Idaho all the way down through Salt Lake down into central Utah. It is capable of up to magnitude 7 earthquakes. And the beautiful mountains that we see in these two images and on the previous slide, that is the product of earthquakes that have occurred over the last 12 million years. So the stunning relief that we see here is because over time, the mountains have gone up, 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 and the basin where Salt Lake is today has gone down. That is what we call a normal fault. So work by the Utah Geological Survey and also the United States Geological Survey tells us that we have a 43% chance of an earthquake greater than a magnitude 6.75 in the Wasatch Front in the next 50 years. So that's a little bit of a sobering thing to sort of take in and to internalize, especially because many of us live right in this area. So how is that probability assessment informed? Well, what you're looking at here is a map of Utah, and each of these lines, these are fault lines, okay? So here's the Wasatch Fault right here, and you'll see that in addition to the Wasatch Fault, there are a number of faults in the area. And this assessment is based on the historical record of earthquakes along these structures, along these faults in the past. So each one of these dots that you see here, this is an earthquake that has happened since about 1850 on one of these faults in this area. So the record of past earthquakes is part of what informs modern day seismic hazards. In addition, we have to look at the actual fault rocks themselves. So when an earthquake happens deep within the earth, you're going to see today that the rocks are transformed. They're transformed in part because of heat. We'll talk about that a little bit more in a second. And it's actually these material property transformations that help us understand. So when Lisa said Alexis studies the mechanics of earthquakes, it helps us understand how the rocks are behaving at depth. For example, in the future, in the next 50 years, when an earthquake occurs. So my research program studies exhumed faults. Again, these are fault rocks that were at depth within the earth where an earthquake occurred, and over time have come up, in part because of other earthquakes and because of erosion and the degradation of the Earth's surface. An example of an exhumed fault system that my research team and I studied is the Wasatch Fault. So many of you have seen this view, perhaps as you're heading down I-15. This is from the Willard and Perry area. This is known as the Brigham City segment of the Wasatch Fault. And these gray rocks here that look slightly chopped up, this is the exhumed Wasatch Fault that was at depth in the past and over time has come to the surface, where my research team and I can study the fault rocks. And so what we do in my research group is we use new technologies or old technologies in different ways in order to document the record of past earthquakes. And the story that I'm going to tell you today is in part about using technology, but it's also a story about developing students' STEM identities. What do I mean by that? I mean how future scientists, they don't see themselves just yet as scientists perhaps, but how future scientists connect, contribute, and engage with research and education. And so what I'm showing you here are two photographs. The image on the left is my research group back in 2015 when we were working in the Wasatch Fault Zone. These are graduate and undergraduate students at Utah State. And on the right here, I'm showing you a field photograph working with middle school students from the Promontory School for Expeditionary Learning in Perry, Utah. So these are 5th and 6th graders. And the work that I'm doing with them is part of my National Science Foundation career grant project. And so what my research team and I do is we give students organic experiences actually doing science, working side by side with members of my research team to help contribute to the research that we are doing. So this work takes place in the field where we go out and have students look at fault rocks from the Wasatch Fault themselves. And it also takes place in the lab where we bring their specimens back to the laboratory and allow them to use modern, state-of-the-art technology to understand something about faults and earthquakes. So this is a photograph of the students working with us together in the scanning electron microscope lab at Utah State University. These students live in the shadow, much like many of you, of the seismically active Wasatch Fault. And they are presently underserved in terms of their understanding about the very real seismic hazards that they face. Okay, so we have to get down to some business here. What I'm showing you on the top part of this slide is a graph of an earthquake from 3 perspectives. There's 3 pieces of information here. Everything here is plotted on the x-axis as a function of time. So I just want to point out that earthquakes are instantaneous events, right? So there is a break in the time scale here, but what you're seeing, all the action that's happening right here, is happening in a matter of seconds. The gray curve here, this is slip velocities. What does that mean? That means how fast 2 sides of the fault are sliding past one another. So you can see here, nothing's happening, and all of a sudden the earthquake occurs, the slip velocity jumps up. The second curve you see here is this term shear stress. Shear stress refers to the stress that's required to overcome friction, or the resistance to those two sides of the fault sliding past one another. So what you see is prior to the earthquake, the shear stress is building up, up, up. That rock is stressed, it's about to fail, and eventually it can't hold it together any longer and it breaks. The rock then dramatically weakens. So the shear stress curve just drops off, and over time it starts to recover. The final curve that you see on this diagram, this is the most important for this talk today. That is the temperature curve, or the red curve right here. And so as this earthquake occurs, as it ruptures and the rocks break, the temperature jumps up and then decays with time. So what we know from prior work is that most of the energy that is given off during an earthquake, given off to overcome that frictional resistance, that shear stress, is given off and dissipates in the form of heat. Now this is important because heat is one mechanism to possibly transform fault rocks at depth within the earth, okay? And the way that my research group and I track these transformations is by looking at minerals that are coating fault surfaces. So the field photograph that you're looking at here are of two hematite-coated fault surfaces. Okay, now, how many of you have heard of this word hematite? Anyone? Oh, yes, okay. All right, so hematite is a form of iron oxide. That is a mineral that is common in most rocks. It's what makes rocks red, okay? So when I think of red rocks, I actually think of one of the places that I used to live in Boulder, Colorado. And so when you're in Boulder, you look back at the flat irons. I know, Mara, you might recognize this. And so the flat irons have, they're red. They're red because of fine hematite in between each of the quartz grains in the sandstone. But hematite can look different. It doesn't always look red, and in this case, it's sort of this jet black, okay? So these surfaces here, these are what we call fault mirrors. We use this term mirror, it's kind of a jargony term, but we use this term mirror because literally when you pick up the rock, you can see your face in it. It's really stunning. And in some places, the rocks have this beautiful peacock iridescence to them. We think that that's because of some of the transformations that happen on these fault surfaces. And so my research team and I, we study these hematite-coated fault surfaces from a number of different perspectives. In order to do this, we first have to go out in the field and whale on some rocks and collect some samples. And so here you can see a photo of me working in the Wasatch Fault Zone. And the middle school students, they do this too. So we take them out in the field, on field trips, up to the Wasatch Fault where they can collect some of their own specimens. And we take some of them and we bring them back to the lab to study them. One of these students that I interacted with during the first field trip to the Wasatch Fault with the Promontory School was a young woman who, after that field trip, told her mom, "I want to be a doctor of rocks." Okay? This is this young woman right here. She became, in the summer of 2018, my field assistant as we collected additional samples to study additional problems in the Wasatch Fault Zone. And so you can see her working in the field. She had actually identified one of these fault surfaces without any prompt from me. And so it's these grassroots organic experiences, and this may just be one person, but they can make a difference on a young person's trajectory and the development of their STEM identity. So in my research group, we use nanotextures. So textures that are down to 1/1,000,000th of a millimeter. And a tool called thermochronology, we'll unpack that in a little bit, to look for evidence of heat and transformations in these fault rocks. And we're doing this ultimately to have an increased understanding of earthquake processes. earthquakes that are happening today, and we're looking at from the perspective of earthquakes that have happened in the past. And as I mentioned before, one of these key tools that we use, one of these sort of new technologies is the scanning electron microscope that we have here at Utah State. This is a tool where you have a column of electrons that shines down or comes down and is introduced to your sample. And the interaction of those electrons with your specimen produces an image. That allows us, okay, these electrons, they allow us to look at our fault rocks up to 300,000 times magnification. Because some of the transformations that are happening, we cannot see with our naked eyes. So we need tools like this. So here's an example of a hematite-coated fault mirror. So you can see this sort of high-gloss, light-reflective surface. And what we have done is we have taken a saw and we've cut down through the specimen, much like you take a knife to cut a birthday cake, so that we could see the interior layers inside. This image on the right is that cross-sectional image from this specimen. So this sharp surface right here, that is the smooth fault mirror surface. Now when we look away from the fault, we see a texture of intergrown hematite crystals and quartz. So this particular specimen is not solely iron oxide, but it also has silica in it as well. So these blue-gray crystals, this is denoting the hematite. The pink here is the quartz. Notice the scale bar, 50 microns. So we are zoomed in here 10,000 plus times magnification. When we look at the fault surface itself, we see a dramatically different texture. So the fault surface is just out of view on this slide, but instead of seeing these somewhat elongate, intergrown hematite crystals, we see what we call polygonal grains. This texture is analogous to a honeycomb. We know something about that here in the beehive state, okay? But it's all of these hexagonal crystals that are fused and sintered together. And this texture, once we saw it, this was the first indication, hey, I think these surfaces are getting hot. And not just, 80 degrees Fahrenheit, but hot enough potentially to melt them and transform the material right at the fault surface. So we are talking about greater than 1,000 degrees Celsius. Now we can look down on the fault surface itself now in plan view using the scanning electron microscope to understand more about how this sample has transformed. And we have a very special detector on our SEM at Utah State known as an electron backscattered diffraction detector. And this is a tool that allows us to map out the chemistry of our fault surface, to see if there's any unique phases or minerals there, and it allows us to understand and map out the crystal structure. So I asked our lab manager, Fanan Shen, to help me acquire electron backscatter diffraction data from our specimen. And she said, okay, well, what should I do to prepare the sample? How should I polish it? Now, this is a technique that requires typically intense hours-long sample preparation where you're polishing the surface that you want to analyze so that you can acquire high-quality data. I said to Fanan, I don't want you to touch it. I want us to use that natural polish that we see on this fault mirror to try to acquire these data. And she looked at me and she's like, okay. I said, okay, let's go for it. So what we were able to do with high resolution scans for the first time is document the presence of another type of iron oxide on these fault surfaces. And so this is a chemical map, so we're mapping out the various minerals that we see on the fault surface. The blue is all the hematite that's there, but we also see this mineral in nanoparticles called magnetite. This is a magnetic mineral that if you put a magnet on it would just stick and attach. This is a significant observation because this tells us again that there were high temperatures on this fault surface. So during very quick, short temperature bursts on the fault, hematite actually changes its crystal structure and can become magnetite. And so the documentation of these particles was another piece of evidence that this particular fault surface got hot in the past. We can interrogate this sample even further at an even finer scale by using a focused ion beam to basically now cut our sample down to the micron scale. So what we did was at the University of Utah, in their nanofab lab, they have one of these tools that allows us to trench out a cross section. This is sort of the ultimate cake cutting knife for very tiny cakes, okay? So we were able to mill out and extract this little cross section, and then it's going to ultimately be placed into a transmission electron microscope, and this is the TEM at the University of Utah. Using this tool, we can then map out the textures, the chemistry down to the atomic scale. So on the left, what you're looking at is this cross section, and this is a chemical map. Again, the blue is the hematite, and we can see now down to the scale of nanometers the presence of this quartz. This quartz we saw in one of the earlier slides is also found in this specimen. But we were curious, is this quartz actually crystalline? Does it have a regular, repeatable structure of atoms? Or is it perhaps itself transformed by the heat? Is it amorphous? And in fact, when we use the TEM and some of the tools with the TEM, now here we are, 10 nanometers. We are now looking at the scale of atoms. What we see here is something that looks like your TV when you can't get a signal. Okay, I know, back in the day. So this image with all of these little dots, this right here tells us that this material is amorphous. You might say, okay, how do you know that? If this silica had been a crystal with an actual crystal structure at the scale of atoms, we would have seen columns of dots lining up according to that crystal structure, and instead we see chaos. So that told us that this silica right near the fault surface is amorphous. In addition, we can probe even further and we find out that in between each of those polygonal grains, there are nanofilms of silica, like a web, that connect into those larger pods of amorphous silica. And so we pull together these observations, and what we have figured out is that during an earthquake that was accommodated on this fault mirror, that there was intense heat during the rupture of that fault surface. The rupture causes all of the pieces of rock to break up. The friction and the interaction of each of those particles causes that temperature to spike. And it's so hot that it melts the rocks. And so that's what this schematic right here is representing. So we have intense heat that is melting and weakening the rocks, and that is important. This phenomena of weakening or dynamic weakening, that is important because that's what allows a rupture, an earthquake rupture, to propagate on a fault. Let's return to this image here that we saw earlier. This is the image of the fault surface, okay? And when I look at this image, I see two polygonal networks. Do you guys see that? How many people see two networks of polygons? Okay, yes, there's a hand. Yeah. So let's look a little closer. The first network of polygons are these black lines. Okay? Those black lines are recessed regions between, they're shadows almost, they're recessed regions between two adjacent transformed polygonal grains. The second network of polygons are these white lines. And it took us a while to figure out what are these white lines? Is it something chemically different about the rock? Is something else going on? And it was a very creative former undergraduate at Utah State, Jordan Jensen, who said, I think that that's topography. I think that that's roughness on the surface. And he's right. It turns out that these white lines represent ridges where material across this fault surface is puckering up into fault rock on the other side of that interface. Now we only have one side of the fault, right? The other side is gone. And it's these networks that tell us that as that heat was decaying away and the temperature was decreasing, the crystals interlocked across the fault surface. That's significant because what that's telling us is as that temperature spike is decaying away, the fault is transforming and it's strengthening. Okay? So it's no longer weak, allowing to that earthquake to propagate, but the earthquake is arresting because the rock is freezing, right? It's solidifying. And so this is important because it's telling us that weakening preconditions faults to strengthen through their material transformations. You might say, okay, well, how is all this relevant for earthquakes? Okay, how is this relevant for earthquakes that have happened recently? Well, we can take the Bluffdale earthquake sequence as an analog. Did any of you feel earthquakes related to this swarm? Yes. Okay, so here we are down near Bluffdale, here's I-15, and each one of these dots is an earthquake that happened on fault rocks at depth within the earth. There wasn't just one earthquake, there was a swarm. So there was original larger earthquakes up to magnitude 3.7, followed by a cluster of what we call aftershocks. And part of the reason I would suggest to you that these dots are all jumping around, okay, in space, meaning on different faults at depth, is because the material properties on this fault right here, after that earthquake, it weakened and then it strengthened. That allows, as stress builds up, another fault to rupture, and then another fault to rupture, and another fault to rupture. So the weakening of the material because of the intense heat, and then the strengthening, is what is controlling the distribution of earthquakes in an aftershock cloud. So this is a field photograph of the Wasatch Fault Zone in the southern Brigham City segment outside of South Willard, Utah. And we see in these fault rocks those very hematite-coated fault mirrors that we just explored together in the previous slides. So this is one of these spectacular fault surfaces right here. And again, indeed, when you pick it up and you look at it, you know, your face, you see it. It's high gloss, light reflective, and this smooth interface, this polishing is happening because of earthquakes. We work with middle school students to collect their own fault mirror samples. And these students have identified some of the best polygonal grains that we have found yet on Wasatch fault mirrors. So this is telling us that on these fault surfaces, there was at some time in the past intense heat related to earthquakes. And so this is another SEM image of what one of those fault surface textures looks like from the Wasatch Fault. Now, the hematite-coated fault surfaces are not the only earthquake rocks in the southern Brigham City segment. We also see these stunning, smooth, silica-coated fault surfaces as well in these exhumed fault rocks. And this is work of master's student Leah Hauser. She has used our SEM to look at these fault surfaces, again, all the way down to the nanoscale. And we see here stunning polygonal grains. In this case, these polygonal grains are not iron oxide, but these are silica polygonal grains. The silica on these surfaces is transforming as well. This image right here on the right, this shows these crystals growing into a void space, almost like a geode. Okay, if you've ever cracked open a geode and you see the sparkling quartz crystals shining back at you, this is what this image reminded me of. And this is important because what this is telling us is at the time that this surface was transforming because of an earthquake, there were fluids around allowing the crystals to grow unimpeded. Now, you might look at these images and say, oh, well, these are amazing crystals. You've used the word crystal here. It must be made up of a regular, repeatable crystal or atomic structure. And indeed, some of these crystals are in fact just that. They are minerals. But we can use the transmission electron microscope to see that some of these particles, these polygonal grains, they're not fully crystalline, as we had first suspected. Here is this staticky TV pattern again, telling us that even though they appear to be crystals, they preserve that amorphous signature. Again, that's really important because it's telling us that these surfaces probably experienced high temperatures as well. One of the very curious observations that Leah made using the transmission electron microscope is the presence of nitrogen in these samples. So what you're looking at here is one of those focused ion beam milled lamellae or cross sections of the fault surface. And this material in light gray, that is the silica. And this dark material here, that is a phase called titanium dioxide. Now, titanium dioxide is not a material that's studied intensely in fault rocks in the earth sciences community, but it is actually a material that is used extensively in photocatalytic work, so making solar cells. And it turns out that when researchers try to increase the effectiveness of photovoltaic cells using titanium dioxide as the substrate, they actually dope their material with nitrogen under high temperatures. So the presence of this nitrogen within the titanium dioxide, something that's never been recognized to the best of my knowledge in fault rocks, in earth science, this is something that has been intensely studied in a completely different field, and we were able to use that information to tell us that perhaps this is another line of evidence that these silica fault mirrors are getting hot. I mentioned earlier in the talk that another tool that we use as sort of a fault rock thermometer, taking the temperature of fault rocks, is this term thermochronology. Embedded in this word is temperature and time. And so my research expertise is actually thermochronology. I study the thermal evolution of rocks, fault rocks through time. The underpinnings of this technique involve radioisotopic decay. So many of you may be familiar with the term geochronology as a tool that is used to figure out when rocks formed in the past. This same tool can be used also as a thermometer. So hematite incorporates trace amounts of radioactive elements, uranium and thorium. Isotopes of uranium and thorium decay spontaneously and naturally to stable daughter products of isotopes of the element lead. This process is not just a one-shot deal. It actually occurs by decay chains. And one of the products of this radioactive decay is the production of helium. Helium is a noble gas. And so that helium, when it's first produced by radioactive decay, is hanging out in the crystal, okay? But over time, if the temperatures get hot, that helium has the potential to diffuse out of the crystal. This is sort of like the balloon that you get for your kid's birthday party, right? And you have this great party, the balloons are at the ceiling, and about a week later you come back and the balloons are all floating around waist level, right? That's because the helium has diffused out of that balloon. Helium at high temperatures, this helium can diffuse out of these hematite crystals. So if we can measure that helium that's left in a crystal, okay? if we can measure these isotopes of uranium. We know the rate that the helium is produced by radioactive decay, and we can solve for time. Maybe thinking, okay, well, time since what? In this case, it is time since helium has been lost or rapidly diffuses out of these hematite crystals because we would suggest the high temperatures that have occurred on these fault surfaces in the past. And so we see helium loss that is occurring because of these temperature spikes. And also, if you think about it, if the rocks have melted, right? If the rocks have completely transformed, that phenomena is actually going to cause helium to be lost from these crystals. So there's a few things going on here. And so what we do is we take these specimens back to the lab and we can extract hematite right from the fault surface. And that's important because when we target this hematite, this is an example of one of these pieces that we analyze. When we target this hematite, it is the material that has experienced, we think, the highest temperatures based on the textures and the highest strain during an earthquake. And so we can take these specimens that we prepare in my lab and that we investigate with the scanning electron microscope to the University of Arizona's Noble Gas Laboratory, where we measure their helium content and their uranium and thorium content so we can calculate time since that helium was evacuated from the crystal structure. So this is work of PhD student Rob McDermott. He has done some of the foundational work in the Wasatch Fault in my research group. And what you're looking at here is a plot of hematite date. So this tool is called the uranium, thorium, helium system, hence this abbreviation right here. The units for this graph are millions of years. So we are talking about documenting evidence for earthquakes that have happened in the past. So this axis is going from 7 million years all the way to present day. And each one of these dots represents an analysis of one of those pieces of iron oxide that Rob first pre-screened with the scanning electron microscope to look for evidence of these high temperature textures. The gray dots are from pieces of the fault surface that did not have any evidence from the textural perspective for high temperatures. And the red dots that you see here, these are aliquots or pieces of the fault material where we identified some of these polygonal grains. The important thing about the pattern that you're seeing here is that most of the aliquots that contain the high temperature textures, they yield the youngest dates. That means most recently, they experienced these high temperatures that allowed the helium to diffuse out of the crystal. So we can pull all of this information together to start to back out a story of these faults, these small faults. I mean, this is only 5 centimeters. These small faults in this network of the Wasatch Fault Zone, or what we call the Wasatch Fault Damage Zone, getting hot at some point in the past. That is telling us that these faults that were at depth within the Earth and are now at the surface, that they accommodated earthquakes sometime in the past. And using the thermochronology, we can begin to pinpoint when those events happened. And so we know that these faults accommodated or had earthquakes on them less than 4.5 million years ago. So when you think back to this diagram, okay, this is now combining the probability map. Here are the earthquake, here are the faults along the Wasatch Front and other fault systems with the historical record of earthquakes or seismicity in the state of Utah. We can now push that record back deeper in time to recognize that faults such as the Wasatch Fault have accommodated earthquakes over the past 4 or 5 million years, and potentially even longer. The other thing that we've learned about in today's talk is that as these earthquakes are happening in historical time, at depth within the Earth, the fault rocks themselves are changing. They're changing because of the intense heat that's generated due to friction during an earthquake. They're changing as they cool from that temperature spike and the materials are transforming and growing in a new and different way. And those fundamental changes to the fault rocks, this is what is controlling how materials in the Earth are deforming and changing at depth during the earthquake cycle. And so with that, I will take any questions that you have, and I want to acknowledge a number of students and postdocs who have made this work possible, as well as a number of collaborators both at Utah State, at the United States Geological Survey, and institutions around the country. This work has been supported in part by the National Science Foundation, the NSF Career Program, and the Southern California Earthquake Center. So thank you.
Fascinating, first of all. Thank you so much. It looks like you're getting a lot of the inputs on what causes earthquakes. What do you think is the future for actually preventing them? You know, in listening to some of the inputs, it would be injecting something, a cooling lubricant into the hot spots. Do you see that? And when I think about the statistics that you put right up front, we have to get there about 57% in less than 50 years to prevent the magnitude that you're talking about. Do you think we will get to that point to be able to surgically hit some of those areas?
Okay, so what Jim is asking is whether there are ways or strategies, technologies that we could use to potentially prevent earthquakes. And you mentioned injection of materials into the subsurface. This is a great question. This is a tricky question because I would suggest that it's injecting material back into the subsurface could actually have some harmful effects, okay? So what I'm thinking about, and some of you may be familiar with, the induced seismicity that has occurred in the mid-continent of the United States. Actually, if you look at a map of earthquakes across North America, say in the last 10 years, most of the earthquakes that are happening today are happening in Oklahoma, okay, and in the mid-continent, because they're actually injecting material back into the subsurface. And what that does is, yes, in some cases, it could potentially lubricate, that was a great word, or weaken faults, but it can also critically stress them to the point, remember that shear stress curve, where all of a sudden it's building up and then that extra pressure and it fails. So that might actually have sort of a counterproductive effect. I think one of the most important things that we can do is, first of all, we need to be aware of the very real seismic hazards that we face. And we need to think about, when we go to continue to build and to develop, where we're building and where we're developing. And also thinking about building code and infrastructure. There are certain things that engineers can do, certain modifications that can be made to buildings, both retroactively and proactively, to make them less likely to completely fail. This is something that's actively happening, say, in California. So I would say that the injection of materials is a possibility, but it could have some unintended consequences that we just need to be aware of. And there are a number of researchers who work on that problem. So, yeah.
I agree with his comments. What a wonderful presentation. And I love how you share your work with the students you work with your collaborators. I mean, you don't just take this by yourself, you just share it. Now, I want to ask a question about the Bluffdale. I live in Vanderbilt along the Wasatch front. And I remember hearing on the news about the Bluffdale earthquake. And I thought in the middle of the night, I I felt some tremors. I felt that my house was shaking. Could that be true, clear and manageable from Bluffdale?
Yep, absolutely. Seismic waves can radiate through the subsurface of the earth, and you could feel them. I mean, you know, the earthquake that happened recently in Tremont was felt by a number of people throughout Cache Valley. So it's absolutely possible. Yeah, and so.
So I should move.
No. I think if you're moving, we're all moving. It's definitely possible that you could feel. I mean, a magnitude 3.7, the energy that's released is getting up there, so it's possible that you could feel that. I would just comment real quick, and I'll take your question, that many of the earthquakes, I didn't really get into this, but many of the earthquakes that I'm talking about here, these are not the magnitude 7s that we're documenting. So you might say that these fault surfaces, like, oh my gosh, is there, on this tiny fault right here, was there a magnitude 7 earthquake? No, these are small earthquakes. We think based on data that we have between a magnitude 3 and a magnitude -3. Tiny little guys that are the aftershock clouds following large earthquakes. Okay, so just to say that earthquakes happen over a range of intensities, right? So, yeah, I just back here.
So my question is on that shear stress curve.
Yeah.
So do we have tools that are in existence so that we can measure how much stress there is and predict when an earthquake will occur?
Yes, so that's a great question. The question is, okay, so there's this curve of shear stress. The resistance is building up, and eventually the rocks are going to fail, and that earthquake is going to take off. And how can we detect that buildup of stress? So there are a number of instruments that are deployed around fault zones. Take, for example, the San Andreas Fault, that monitor the position of rocks. So GPS. Okay, that monitor the position of rocks and how they're moving as two faults slide past one another. So faults, not all faults rupture by earthquakes, but they might creep. And so we can detect some of that slipping that's happening very slowly on those instruments. And we can use GPS and other tools to help us see how faults are slipping slowly and perhaps bleeding off some of that stress, and faults that are locked, okay? And work of the USGS and the Utah Geological Survey, I mean, part of what they do is monitor that activity in partnership with universities in Utah. They monitor those changes to the Earth's surface. And I would just suggest to you that part of it is knowing something about the longer term record of deformation to say, hey, this fault hasn't had an earthquake in 2,000 years. So it's perhaps overdue for an earthquake. Yeah, that's a great question. Yeah.
Do these clusters of small earthquakes help to relieve the stress so it doesn't build up to a 6 or 7?
Okay, that is an excellent question. One of the things that happened in the sort of the aftermath of the Bluffdale, or sort of the period after the Bluffdale earthquake sequence is, you know, someone said, well, oh, is this the predictor for the big one? Is the big one coming? Or have we sort of staved off the likelihood that the big one's going to happen because we've had these small earthquakes? Those earthquakes that magnitude 3 and smaller, there was not enough energy released to basically calm the system down. So I would suggest that the answer to your question is it depends. It depends on the system. So for example, think about the Ridgecrest earthquake. Was anybody in California and they felt the Ridgecrest earthquake? Yes. Okay, so there was a 6.4 and a bunch of aftershocks, right? And then all of a sudden, boom, 7.1. Had a number of friends that were actually out there, colleagues that were, you know, raced out there after the 6.4, and then they were in the midst of the 7.1 that happened, right? So you know, you might say, well, how is that happening? Well, part of part of the map of all of those aftershocks, that's because fault zones are incredibly complex, and how that stress is transferred around is different from aftershock sequence to aftershock sequence. But the maps of those earthquakes, for example, and the pattern of those aftershocks, it was very impressive and is pointing to, quite voluminous fault damage. So sometimes maybe yes, but most of the time no. Yeah.
So it's a firm maybe.
It's a firm maybe. Yeah, it's a firm maybe. Yeah.
One point that the California earthquakes are strike slip type quakes versus the graben and horse type that we have in the Rocky Mountains. My primary question is, are you sharing your information with the state engineer and the various counties? I live in the city of Holiday, and we've got a proposed building project in there in a known fault area where they want to build a 9-story building. Bad idea.
Okay, so a couple of things there. I just want to speak to that one point. The first thing is, the gentleman here said, hey, the Ridgecrest earthquakes, those were strike slip faults. Yes, exactly. Faults occur in all forms and fashion. And interestingly, the way in which the ground shook there was a little bit different because of all the unconsolidated sediments and the depth of the earthquake. So it's definitely different. It depends on what rocks you have at depth. That being said, here in the Wasatch, we're sitting on the basement that's been exhumed is hard rock, right? So you have to know something about what the material properties are with depth to know what how those rocks are going to be transformed. To the second part of your question, I have not yet shared this information with city officials. This is work that just began in the last couple of years, and I think we have a little bit of a ways to go and a much richer data set that we need to collect to provide even more insight to those people, but that would be a great group to interface with. Yeah, yes?
How far is the heat distributed away from the face?
Did you guys hear that question? She wanted to know, how far does that heat travel away from this interface? Centimeters. Not far. For small earthquakes, centimeters. Has not gone far. But the larger the earthquake, the more intense that heat penetration is. So yeah, we're talking centimeters, and so that's why we have to go right here to the fault surface. We can't work down here. That's an excellent question. It's an exam question. Yeah. That's good. No, it's good. It's like a great question for my students. Yeah. Yeah. Okay. Thanks, Lisa.
You can imagine what it's like for those middle school students when they go out into the field with Alexis. This is what being an NSF Career Awardee is all about. It's about engaging people in what we do, and Alexis is one of our very best. And so I look forward to the great things she's going to do in the future, both with her research and integrating students into that work. And so with regard to Sunrise Session, we invite you to join us again in the new year for other Year of the Woman Sunrise speakers, when we'll be having Dr. Mara Hagan and Dr. Tammy Firth speak to us during spring 2020. The first one of those is on January 28th, and that's Mara Hagan, the Dean of USU's College of Science, and a recent inductee into the National Academy of Sciences, the first person from Utah State University ever to receive that recognition. So we look forward to tomorrow's talk. Furthermore, this summer, we're going to be excited to announce a new direction and approach for Sunrise Sessions. It's something we've been working on and discussing with regents over the last several months. And so we're looking forward to finding new ways to deliver to you the best and most impactful research stories from Utah State University. You can learn more about Sunrise Sessions by subscribing to our mailing list, which is on our website, sunrise.usu.edu. And with that, I thank you all for coming and have a great day.